Cool.
This meeting is being recorded.
One of the simplest BRDF is Lambertian model, which is a perfect diffuse surface that scatters incident illumination equally in all directions. It's a reasonable approximation for many real-world surfaces, such as paper or matte paint. Lambertian model captures the behavior of diffuse materials relatively well. And the approximation tends to perform worse for light arriving at a grazing angle, where specular reflection causes a noticeable deviation from uniformity. And macrofacet models presented in 9.6 account for such details, which those are also used in real-time rendering. So yeah. It's interesting that surface is created from, I will not try to pronounce that, PTFE powder are known to be particularly good Lambertian reflectors. So they are commonly used to calibrate lab equipments. So they have this diffuse BXDF class. It just contains a sampled spectrum. Constructor takes a reflectance, it takes a sample strip spectrum with value in range 0 to 1. Specify the fraction of the incident light that is scattered. And it just gets stored. And the PDF is just a constant. It requires a normalization factor equal to 1 over pi, so that the total integrated reflectance equal R. This is hemisphere, right? And yeah, I think it's hemisphere integration. I will trust this math to be correct. But anyway, it's not hard math to derive. With this correction, the F implementation is given by so if it's not the same hemisphere, the input and output will just get 0. Yeah, otherwise we return the constant. And sampling function returns an invalid sample if the color specified reflection components of BSDF should not be sampled. Otherwise, it draws a direction from a suitable distribution and return all the sample related information via a BSDF sample instance. So okay, so we have a sample flag. It's basically check whether it has reflection. If it did not, we just wouldn't return. And this computes the PDF and the input Oh yeah, because because they they use the output as input for PBRT that we just learned last section, and so that's why they calculate the input from the output, but not actually from the output in this case because there's a Lambertian, so we just samples hemisphere. Working in a canonical reflection coordinate system greatly simplifies the central sampling step. And in particular, a direction generated by sample cosine hemisphere can be directly used. And we just need to pay attention that the input and output lie in the same hemisphere by checking their Z value. Yeah, we don't even need to do dot product, just use the Z value. Although the Lambertian BRDF is uniform over the hemisphere, BSDF are sampled in the context of light transport equation. Where the BSDF is multiplied by the incidence radiance and the cosine factor. It is worthwhile for BXDF to include the cosine factor in their sampling distribution if possible. So cosine hemisphere seems to have less noise. Yeah, it's improved mean square error by a factor of 2.34 for this testing. So decrease in noise. They sample cosine weighted hemisphere. Yes. And also they need to adjust for the PDF. Which just call the cosine hemisphere PDF helper function. So comment, I think because the cosine hemisphere weighted shapes the distribution of the ray from being completely uniform. Yeah, it's exactly important sampling, right? That's why they need to change PDF. It's no longer a constant. Yeah. So next chapter, specular reflection and transmission. So following the discussion of diffuse surfaces with their perfectly uniform reflectance, we now turn to the opposite extreme specular material that only reflect light into a discrete set of directions. So the following a review of physical principles underlying such material, and we will introduce concrete BXDF in 9.4 and 5. Okay. So next time. We initially focused on perfect specular surfaces with many real-world materials are fairly rough at a microscopic scale. So 9.6 and 7 will generalize our understanding. So for the most part, this book concerns with geometric optics. So which describes the scattering and transport of radiance along rays. We are doing ray tracing after all, so yeah, not wave tracing. So it's an approximation of the wave nature of light. Yeah, it's a pretty good one because visible light waves occur at the scale of negligible compared to the size of object rendered in PBRT. So yeah, wave-like phenomena normally do not manifest in rendered images. But to understand and model what happens when light strikes surface, it's helpful to briefly turn to this deeper understanding of light in terms of waves. So you've seen wave optical result within an overall geometric simulation is often possible. It become a common pattern. So electromagnetism describes light as oscillation of electric and magnetic fields. Yeah, this term refer to vector fields, which like assign fluid vector to every point in space. These vectors describe force that a small charged particle would feel due to such a light wave passing through it. For our purposes, only the electric field is interesting. And the charged particle will be influenced by this force is electrons surrounding the nucleus of, it's an electron, basically. When a beam of light arriving at the surface, it stimulates the electrons, compressing the material of the atoms, compressing the material, causing them to begin to oscillate rapidly. This moving electron charges induce secondary oscillation in the electric field, whose superposition is then subject to constructive and destructive interference. This constitutes the main mechanism in which atoms reflect light. Though the specific of this process can vary significantly based on the type of atom and the way in which it is bound to other atoms. So the electromagnetic theory of light distinguishes the following three major classes of behavior. So yeah, dielectric materials, which is electric insulator, like glass, water, oil, and air. In such materials, oscillation electrons are firmly bound to the atoms. Yes. Yeah, water can be conductive if adding something, ions like salt, but it's irrelevant. And second class of conductors are metals. There are also semi-metals like graphite. And some of the electrons can freely move within their atomic lattice. And so oscillation induced by incident the electromagnetic wave can move electrons over a large distance. At the same time, migration through the lattice dissipates some of the incident energy in the form of heat, which causes rapid absorption of light wave as it travels deeper into the material. And total absorption occurs within the top 0.1 millimeter of the material, and only extremely thin material metal films are capable of transmitting appreciable amount of light. Yeah, we ignore this part and just treat metallic surface as opaque. And third parts are semiconductors, such as silicon, which exhibits properties of both dielectric and conductor. For example, silicon appears metallic in visible spectrum. At the same time, it's transparent. And we do not consider semiconductors in PBRT, though if we add another BXDF handle them, it will be easy. Semiconductors are like not that common in real life, so not that common in random image anyway. So index of refraction. So commonly seems the distinction applies mostly to transmission, conductors being opaque. Dielectrics have some amount of transmission. I'm not that good at physics. So yeah, from this paragraph, you are correct, but I am not that good at physics to comment on this.
Yeah, that's kind of, getting into, yeah.
So index of refraction. So when instant light waves stimulate an electron, the oscillation induces its own electromagnetic oscillation. The oscillation of this re-emit light incurs small delay compared to the original wave. Oh, the compound effect of many such delay within the solid material causes the light wave to travel at a slower velocity compared to the original speed of light. Oh, refraction is caused by this? Interesting. So slow reduction is commonly summarized using the index of refraction. Material with IOR of 2 probably light at half of the speed of light. And for common materials, the value is in range of 1 to 2.5. We use a Greek letter nu. Oh, eta, okay. I never know how to pronounce Greek letters. Just try random stuff. Light waves undergo significant reflection when they encounter boundaries with a sudden change in the IOR value. So an air diamond interface with a high IOR difference of 2.4 will appear more reflective than air glass surface with a difference around 1.5. So IR also provides a main mathematical explanation of why we perceive objects around us. It's because the IR differs from the surrounding media. Specific value of eta computes appearance of surface, and a good estimate of this value is important for physically based rendering. So some of the common value vacuum is 1, just because the light speed, and air at sea level is almost 1. And ice and water have some higher values. Glass have higher, and diamond is really high, basically. So 9.1 provides IOR values for a number of dielectric materials. And also it's wavelength dependent IOR for few materials. That seems to be that different across the wavelengths. PBRT also include wavelengths dependent IORs for various materials can be referred to in the file format. So in the following, we assume that IR on both sides of the surface in question is known. We first review in which direction light travels following an interaction, which is described by the law of specular reflection and Snell's law. How much the scattered light travel in those directions is given by Fresnel. So given an incident light from a direction theta I and phi I, a single reflected direction theta I and phi R follows a interaction with perfect specular surface is easy to characterize. Yeah, it makes the same angle with the normal as incoming direction and rotate around 0.8 degree, 180 degrees. So yeah, so theta don't change the same angle, and then phi is rotated by pi. This direction can also be computed using vectorial arithmetic instead of angles, which is more convenient in subsequent implementations. Yeah, there's there was an interesting article called "Avoiding Tricks." So basically, just we don't need to use that much trigonometries to compute stuff. So instead, we can decompose vector omega that lie in the plane into the parallel and vertical. Those vectors are easily computed because n and omega are normalized. And parallel is the cosine theta of n, which is just normal vector dot the omega. and then times the normal vector. And also the perpendicular component, we just use the subtraction. And so the reflected ray is just like have two components, and then the parallel component don't change, the perpendicular component gets mirrored, and the result is this. To come to this reflect function, it's commonly used in shaders. But I think if they use a normalized coordinate system that a normal vector is always a fixed value, this can even be simplified more. Like, yeah. And Snell's law. At a specular interface, incident light with direction theta I phi I about a surface normal refracts into a single transmitted direction theta t phi t located on the opposite side of the interface. And this process is described by the Snell's law. Depends on the direction and IOR value on both sides. And there's two images like specular reflection and also refraction. Snell's law states that, yeah, this. If the target media is optically denser, that means the refracted light bent towards the surface normal. And Snell's law can be derived using Fermat's principle. And this is wavelength dependent IOR shows the interesting. Where different light at different wavelengths get scattered in different directions. Neat. No, my cat comes with the sorry. My cat's just come to the keyboard now. He's purring. Goodbye. And the index of refraction varies with respect to wavelengths. Yeah. And light consists of multiple wavelengths will split into multiple transmitted direction at the boundary between two different media, which dispersion. So it's this effect, basically. One useful observation about Snell's law is that it technically does not depend on precise value of those IOR, instead just on their ratios. I think that's what ray tracing in weekend does. It does not model like light transport between two different materials with different IR. It's always just models air and other materials. So then it's just always using one value instead of two. Yeah, where the relative index of refraction specifies the proportional slowdown incurred when light passes through the interface. We will generally follow the convention that relevant laws and implementation are based on this relative quantity. As with law of specular reflection, we should now derive a more convenient vectorized form of this relationship in 9.10. So given an incident direction omega I and a surface normal n with angle theta I between them, and also an output, we can use Snell's law to find the perpendicular component and then parallel component, and then given the normalized result omega t. So the trig expression above are closely related to the parallel and perpendicular components of incident and transmitted direction. Oh yeah, because sine is this, so it's the perpendicular component. Yeah. So equation 9.3 can be written as this. And then the perpendicular component can be computed as this. And the parallel components point into the direction of negative n. And magnitude is given by cosine theta t. Cosine theta t. So this. And at the end, we just get this. So the function refract computes refracted direction omega t via equation 9.4. given incident direction omega I, surface normal and the same hemisphere as omega I. Relative index of refraction eta. Adjusted relative IOR may be returned via the eta pointer. Eta, we will discuss the details shortly. Oh, I guess this is to use later. The returns are Boolean because sometimes there were just no refraction. So yeah. The functions convention for relative index of refraction eta is slightly different from the previous definition. Specify the IR ratio of the object interior relative to the outside. As indicated by the surface normal n that anchored the spherical coordinate system of quantities like theta I or theta t. When the incidence rate lies within the object, this convention no longer compatible with our previous use of Snell law, assuming positive angle cosines and a relative IOR. They detect this case and then just flip. Cosine, so the cosine of angle theta between a direction omega and the geometric surface normal indicate whether direction is pointed outside the surface or inside the surface. Yeah. Standard reflection coordinate system, this test just require checking the z component of the here is positive, but omega prime is in the lower hemisphere, so it should have a negative data. So yes, if cosine is less than 0, then we just flip the index, flip the IOR, also flip the vector. Sometimes useful for the color of refraction to know the relative IOR along the ray while handling the case where the ray arrives from the object's interior. So to make this accessible, we store out pointer basically. How the cosine of the transmitted angle can be computed. It can be derived from equation 9.3 and identity like sine square and cosine square is 1, which Wait, what is 9.3? Oh, just Snell's law. Yes. And also one potential complication is that when light travels into a media that is less optical dense, yeah, sometimes we just don't have a refraction at all, so it's just total internal reflection. So rise when theta is greater than the critical angle. In which case, this function, the square root just become negative, so we just don't have a solution. It's easy to experience personally in a swimming pool, observing the air-water interface from below. Reveals a striking circular pattern that separates a reflected view of outside from pure reflection of the pool's interior. Huh. I don't know. Maybe I will try it next time I go to a swimming pool. I think that's how fibers, like optical fibers, works, just to not lose energy along the way, just because it's total internal reflection. But in the case of total internal reflection, the refracted direction is undefined and the function returned false to indicate this. I'm disappointed that they don't use optional like this. They have optional defined somewhere, which even works on CUDA, but they don't use it in this function. Yeah, anyway, for now, equation. Yeah, where the light travel and then is how much. Light is normally both reflected and transmitted at the boundary between two materials with different IOR. Though the transmission rapidly decays in the case of conductors. We must account for the fraction of reflected and the transmitted light, which is also directional dependent and cannot be captured by a fixed per surface scaling constant. And the Fresnel equation, which are solution to the Maxwell's equation at smooth surface, specify the precise proportion of reflected light. I don't want to skip this part. Oh, they don't, yeah, because they don't use approximation. They use the actual Fresnel's equation. That's why it's so complicated. Maybe let's just skip this part for now because it's already about an hour.